somewhere far beyond the familiar light of our sun, beyond the planets, beyond Neptune, beyond even the faint outer edge of the solar system, there was a small object moving through the dark. It was not a planet. It was not a moon. It was not a spacecraft. It was something older, colder, and far more silent. A piece of frozen matter, drifting alone through the space between stars. For a very long time, no one saw it. There were no oceans beneath it, no blue sky above it, no sunrise warming its surface. No world to belong to. It moved through the deep black of interstellar space, where the stars are so far apart that even light can begin to feel lonely. And yet, this object was not empty. Locked inside its ancient ice were chemical traces from another place, another beginning, another star system. It may have formed in a cold, distant region around a star we will never see, a star that may still be shining somewhere in the Milky Way, or perhaps a star that died long ago, leaving behind only scattered fragments of the world it once tried to build. This small frozen traveler carried no message written by intelligence, no signal, no design, no intention. And still, in its own quiet way, it carried a story older than Earth, possibly older than our sun, a story written not in words, but in water, carbon, ice, and dust. For billions of years, it may have wandered without a home, crossing the invisible spaces between solar systems. It passed through darkness that no human eye has ever seen. It moved beneath constellations that would have looked different from every point along its journey. It may have watched stars be born in the distance, and others fade away into silence. But it did not stop. It could not stop, because long ago, something had thrown it away from its original home. Maybe it passed too close to a giant planet. Maybe, in the young chaos of another solar system, gravity reached out and changed its fate forever. A small, icy body, once part of a family of worlds, was pushed onto a path with no return. From that moment on, it no longer belonged to any star. It became a wanderer. And then, after an amount of time almost impossible to imagine, its path brought it here. Toward us. Toward the sun. Toward the quiet, familiar neighborhood of planets we call the solar system. At first, nothing seemed different. Earth continued turning. The moon continued circling. Mars moved along its dusty orbit. Jupiter and Saturn kept their ancient rhythms in the outer dark. And somewhere in the night sky, hidden among thousands of points of light, a faint visitor was approaching. It was small. It was dim. It was easy to miss. To human eyes, it was invisible. But modern telescopes are built to notice the things we cannot. They scan the sky again and again, comparing one image to the next, searching for anything that moves against the fixed background of stars. Most of the time, what they find belongs to our own solar system, an asteroid, a comet, a distant object following a long, slow orbit around the sun. But sometimes, a point of light does not behave the way it should. Sometimes, it moves too fast. Sometimes, its path is too open. Sometimes, when astronomers trace its motion backward, the trail does not curve neatly around the sun. Instead, it leads outward, past the planets, past the boundary of our solar system, back into interstellar space. That is when a simple dot becomes something much stranger. That is when the sky reminds us that our solar system is not sealed off from the rest of the galaxy. It is not an island. It is more like a harbor, a quiet harbor, floating in a vast galactic ocean. Most things in this harbor belong here. The planets, the moons, the asteroids, the comets that return again and again after thousands or millions of years. They are part of the sun's extended family, bound by gravity, moving in long arcs through time. But every once in a while, something passes through that was never born here. Something from another shore. Something that does not slow down enough to stay. Something that enters the light of our sun only briefly, reveals a little of itself, and then leaves forever. This is what made the visitor so extraordinary. Not its size, not its brightness, not any danger it posed to Earth. It was extraordinary because of where it came from. It had crossed the invisible border between star systems. It had entered the realm of the sun as an outsider. A traveler from another star. Astronomers would eventually give it a name, 3I/Atlas. The name is quiet, technical, almost cold. But behind that name is one of the most poetic facts in modern astronomy. The I stands for Interstellar, and the number means it was only the third known object of its kind, ever confirmed passing through our solar system. The third visitor from beyond the sun. Before it, there had been others. One was strange and elongated, moving so quickly through the inner solar system that scientists had only a short time to study it. Another was clearly comet-like, carrying a glowing coma as it passed through. And now, 3I/Atlas had arrived. Another piece of the galaxy, briefly crossing our path. But this visitor was not just another interstellar object. As the observations continued, scientists began to realize that its chemistry was unusual. Its ice did not look quite like the ice of comets born around our sun. Its hidden ingredients seemed to point toward a different kind of birthplace, a colder place, a more ancient place, perhaps a region of the Milky Way that formed under conditions unlike the ones that shaped Earth, Jupiter, and the familiar comets of our own cosmic neighborhood. And that is where the story becomes deeper, because 3I/Atlas was not simply passing through space. It was carrying evidence. Evidence of another solar system. Evidence of how worlds may form around other stars. Evidence that the ingredients of planets, oceans, and comets may vary across the galaxy in ways we are only beginning to understand. Imagine holding a snowflake that did not fall from Earth's sky, but from a storm around another star. Imagine touching a grain of ice that may have formed before the sun existed. Imagine watching a silent object drift past us, knowing that inside it are clues from a place no spacecraft has ever visited, and perhaps never will. That is what 3I/Atlas offered. Not answers to everything. Not a message from an alien civilization. Not a warning, but something quieter, and maybe more profound. A natural relic, a frozen memory, a visitor from the dark between stars. And for a brief moment, our telescopes saw it. For a brief moment, it entered the light. For a brief moment, the solar system was visited by something that did not belong to it. But how did we notice it? How did a faint moving point in the sky become one of the most important comet discoveries of its time? And how did astronomers know that this object was not just another comet from the distant edge of our own solar system? The answer begins with a telescope scanning the night sky over Chile and a dot that refused to follow the rules. The story of 3I/Atlas did not begin with a dramatic flash in the sky. There was no bright fireball over a city, no sudden warning, no object visible to millions of people looking up from their backyards. It began quietly, as many of the most important discoveries in astronomy do, with a small point of light. On July 1st, 2025, a telescope in Chile noticed something moving against the stars. The telescope was part of ATLAS, the Asteroid Terrestrial Impact Last Alert System, a network designed to scan the sky again and again, searching for moving objects near Earth. Most of the time, systems like this are looking for asteroids, small bodies, faint bodies, pieces of rock and ice moving through the inner solar system. The work is patient, repetitive, almost meditative. The telescope takes an image of the sky, then later it takes another. The stars remain almost fixed, tiny points scattered across the blackness. But objects inside the solar system shift. They slide slowly across the background, leaving behind the first clue that they are closer than the distant stars. Most of these moving points are familiar in one way or another. They may be asteroids orbiting between Mars and Jupiter. They may be comets returning from the distant cold beyond Neptune. They may be small bodies passing through the inner solar system on long but still bound paths around the sun. But this object was different. At first, it was only a faint moving speck. Something so small in the data that it would have meant almost nothing to most people. A tiny motion, a change in position, a dot that was here in one image and slightly there in the next. But to astronomers, motion is language. A moving dot can tell a story. Its speed tells part of it. Its direction tells another. And when enough observations are gathered, the path begins to reveal where the object has been, where it is going, and whether it belongs to the sun. That is when the quiet discovery became strange. The object was moving quickly. Not impossibly quickly, not magically, but fast enough to raise questions. Astronomers began calculating its orbit. They measured its position again and again. Each new observation tightened the path. Each new point in the data made the shape of its journey a little clearer. And the more clearly that path appeared, the less it looked like the path of an ordinary comet. A normal comet in our solar system may have a very long orbit. It may travel far beyond Neptune. It may disappear for thousands of years before returning. Some comets come from the Oort cloud, a vast and distant shell of icy bodies surrounding the sun. Their orbits can be enormous, stretched so far into the dark that they seem almost like visitors from interstellar space. But they are still tied to the sun. They are still part of the sun's gravity. They may leave for a long time, but eventually, they turn back. This object did not seem to be turning back. Its path was open. It was not a closed loop. It was not a long ellipse, reaching into the outer solar system and then returning. It was a hyperbolic trajectory, the kind of path an object follows when it is not bound to the sun at all. In simple terms, it was not orbiting our star. It was passing through. That one detail changed everything. Because if an object is moving too fast to be captured by the sun, and if its path cannot be traced back to any ordinary region of the solar system, then there is only one conclusion left. It came from outside, from interstellar space, from the darkness between stars. Soon, the object received its name, 3I/Atlas. The name sounds technical, but it carries an extraordinary meaning. The 3 means it is the third confirmed object of its kind. The I means interstellar, and Atlas honors the survey that first found it. So hidden inside that short name is a sentence that feels almost impossible. The third known interstellar object ever detected passing through our solar system. Only the third. After all the centuries of human astronomy, after all the telescopes, observatories, sky surveys, and spacecraft. Only 3 known objects had been confirmed as visitors from beyond the sun. That is what made 3I/Atlas so rare. Not that it was large, not that it was bright, not that it threatened Earth. It did not. It was rare because it was a piece of another star system, crossing ours for only a short time. And perhaps what makes this even more humbling is how easy it would have been to miss. A century ago, maybe no one would have seen it. 1,000 years ago, it could have passed silently through the inner solar system, warmed slightly by the sun, formed a faint coma, and then vanished back into the dark without a single human being ever knowing it had been here. Even now, we noticed it only because our machines are patient. Because telescopes keep watching while we sleep. Because somewhere in the dry, dark skies of Chile, a system was scanning the night not for beauty, but for motion. And there it was, a dot that did not belong. Once the discovery was reported, astronomers around the world began looking backward. This is one of the quiet miracles of modern astronomy. After something unusual is found, scientists do not only watch it going forward, they search old images, old surveys, old data. They ask a simple question: was it already there before we noticed it? And often, the answer is yes. A faint object may have crossed the field of view of another telescope days or weeks earlier. At the time, it may have gone unnoticed, just another weak signal in a vast sky. But after the orbit is known, researchers can return to those older images and find the same object waiting in the data. Not newly arrived, not newly created, just newly recognized. This is what happened with 3I/Atlas. After the official discovery, earlier observations were found in archived data. The trail of the visitor could be extended backward, giving astronomers a longer arc of motion and a clearer view of its path. And with each recovered observation, the conclusion became stronger. It was not from here. It had entered the solar system from beyond the sun's domain. And now, for a brief season, humanity had the chance to study it. Think about how strange that is. An object may wander for millions or billions of years between stars. It may cross distances so large that human language begins to fail. It may spend almost all of its existence in darkness, far from warmth, far from planets, far from any place where liquid water could flow. Then, by chance, it passes near one ordinary yellow star, our star. And for a few months, under the gaze of telescopes, it becomes knowable. Not fully, never fully, but enough. Enough for us to see its motion. Enough for us to measure its light. Enough for us to ask where it came from. And perhaps enough to discover that its chemistry carries the fingerprint of a birthplace unlike our own. But before scientists could read that chemical fingerprint, they first had to understand the meaning of its path. Because the first great mystery of 3I/Atlas was not what it was made of. The first mystery was its motion. Why was it moving this way? Why was it not looping back around the sun? Why did its path look less like a member of the solar system and more like a traveler crossing through it? To answer that, we need to look at what it means for any object to belong to a star. We need to understand the invisible architecture of gravity, the quiet boundary between a comet that is ours and a comet that came from somewhere else. To understand why 3I/Atlas was so unusual, we have to begin with something invisible: gravity. Every object in the solar system is moving through a landscape shaped by gravity. We cannot see this landscape directly, but everything follows it. The planets, the moons, the asteroids, the comets, even dust. They are all traveling through the sun's invisible field, guided by the pull of the star at the center. Earth follows its path once every year. Mars takes a little longer. Jupiter moves slowly, like a giant clock hand in the outer dark. And far beyond the planets, countless icy bodies also move under the sun's influence, some in wide, ancient orbits that take them into the deep cold for thousands or even millions of years before they return. This is how most comets belong to the solar system. They may seem like visitors when they appear in our night sky. They may arrive from far away, glowing with tails of gas and dust. They may vanish again into darkness for longer than recorded history. But if their path is closed, if gravity bends them back toward the sun again and again, then they are not strangers. They are distant family. They belong to our star. A comet from the outer solar system can travel so far away that, for most of its orbit, the sun would look like just another bright star. It can spend nearly all of its existence in frozen darkness, and yet, even at those extreme distances, it remains tied to the sun by a thin, invisible thread of gravity. It leaves, but eventually it returns. 3I/Atlas was different. When astronomers measured its motion, they found that its path was not a closed loop. It was not an ellipse, stretched out across the solar system. It was not the kind of orbit that would take it away for a long time, and then bring it back. Its path was open. It was moving through the solar system on a trajectory that would carry it in, around the sun, and then out again forever. This is what astronomers call a hyperbolic path. The word may sound technical, but the idea is simple. Imagine throwing a ball gently into the air. It rises, slows down, and falls back. It did not have enough speed to escape Earth's gravity. Now imagine giving that ball an impossible amount of speed, enough that Earth's gravity could slow it, bend its path, but never pull it back. The ball would not orbit Earth. It would escape. A similar idea applies to objects moving near the sun. If an object is bound to the sun, it follows a closed orbit. It may be round or it may be stretched, but it remains part of the solar system's gravitational family. But if the object is moving too fast, the sun can bend its course without capturing it. It passes through. That is what 3I/Atlas was doing. The sun was not its home. The sun was only a place it encountered along the way. This is the first reason scientists knew it did not come from our solar system. Not because it looked strange, not because it was glowing in an impossible way, not because it behaved like something artificial. Its motion told the story. A natural object can be mysterious without being unnatural. And 3I/Atlas was mysterious in the most scientific sense. Its path did not match the story of a body born around our sun. To picture this, imagine the solar system as a vast, quiet harbor. The planets are large ships moving in steady circles around a central lighthouse. Asteroids are smaller boats, drifting in belts and clusters. Comets are long-distance travelers from the edge of the harbor. Some disappear into fog for thousands of years, but their routes still curve back toward the light. Then one day, a vessel appears from the open ocean. It does not follow the harbor lanes. It does not slow down enough to dock. It simply crosses through the harbor, carried by a path that began somewhere far beyond the map. For a short while, everyone can see it. Then it leaves. That is 3I/Atlas. A traveler through the sun's harbor. A body from another sea. This does not mean it ignored the sun completely. Nothing can pass through the inner solar system without feeling the sun's pull. As 3I/Atlas approached, solar gravity bent its path. The sun changed the direction of its motion, just as a massive planet can bend the path of a spacecraft during a gravity assist. But bending is not the same as capturing. The visitor was moving too quickly to become part of the solar system. The sun could turn it. The sun could warm it. The sun could awaken its ice. But the sun could not keep it. And that is one of the quiet tragedies of interstellar objects. We do not get to study them for long. A comet born around our sun may return in the distant future. Even if no one alive today ever sees it again, some future generation might. Its orbit may be predictable. Its story may continue in cycles. But an interstellar visitor gives us only one chance, one crossing, one brief season of observation. Then it is gone. This is why 3I/Atlas mattered so much. It was not merely another icy object in the sky. It was a sample from outside the solar system that had come close enough for our telescopes to study. Not close enough to be dangerous. Not close enough to disturb Earth. But close enough to become visible to our instruments. Close enough to let scientists measure its brightness, its motion, and eventually, the gases rising from its surface. And from those gases, they could begin to ask a deeper question. If this object did not come from here, then where did it form? Somewhere in the Milky Way, there was once a place where 3I/Atlas was born. Perhaps it began in a cold disk of gas and dust around a young star. Perhaps it formed among countless other icy fragments, in the outer region of a planetary system still under construction. Perhaps it once belonged to a swarm of comet-like bodies, circling a star that may have looked nothing like our sun. We do not know the name of that star. We may never know. The galaxy has hundreds of billions of stars, all moving around the center of the Milky Way. Over millions and billions of years, their positions change. A small object ejected long ago would not carry a return address that we can easily read. Its path through our solar system tells us that it came from outside, but it does not point neatly back to a single home. The trail has been stirred by time, by gravity, by the motion of the galaxy itself. Still, 3I/Atlas carried clues, not in its orbit alone, but in its material. Because comets are not just objects. They are archives. They are cold storage. They preserve ingredients from the environments where they formed. Water ice, carbon-bearing molecules, dust grains, volatile compounds that freeze in the dark and escape when warmed. In our own solar system, comets are often described as leftovers from the formation of the planets. They are remnants from the early disk of gas and dust that surrounded the newborn sun. Studying them helps scientists understand what the solar system was like before Earth had oceans, before Mars had valleys, before Jupiter had finished shaping the outer worlds. But 3I/Atlas was different. If it was truly interstellar, then it was not a leftover from our beginning. It was a leftover from someone else's, a fragment from another planetary system, a frozen witness to another origin story. And that makes it one of the rarest kinds of objects we can study. Because usually, if we want to learn about other star systems, we have to observe them from far away. We watch planets dim their stars as they pass in front. We study disks of dust around young suns. We measure light, motion, heat, shadows. But here, the galaxy delivered a physical piece of another system into our own neighborhood. A natural messenger. Not a message in the way humans usually imagine one. No symbols. No language. No intention. But a messenger in a deeper sense. A piece of matter shaped by conditions around another star, traveling through space until it entered the reach of our telescopes. This is why the discovery of an interstellar comet feels so different from the discovery of an ordinary comet. An ordinary comet tells us about the deep history of our solar system. An interstellar comet tells us that our history is only one version of a much larger story. It suggests that planet formation is not a single recipe repeated exactly the same way everywhere. Different stars are born in different environments. Different disks cool in different ways. Different regions of the galaxy contain different mixtures of elements. Some systems may be rich in carbon. Some may be poor in heavy elements. Some may form comets in regions far colder than the place where our own comets formed. And if we can read the chemistry of one visitor, we may begin to glimpse that diversity. But first, we have to be careful. It is tempting to look at an interstellar object and fill the silence with imagination, to make it stranger than it needs to be, to turn mystery into speculation. But the real story is already strange enough. A small body, born around another star, was somehow thrown out of its home system. It wandered between stars for an unknown length of time. Then, by chance, it crossed the inner solar system while human civilization had the instruments to detect it. That is not science fiction. That is the universe being larger, older, and more connected than we usually feel in daily life. And the more scientists studied 3I/Atlas, the more the question shifted. It was no longer only, how do we know this object came from outside the solar system? The better question became, what kind of place could have made it? Because the path told us it was a visitor, but the ice would tell us what kind of home it once knew. And to understand that home, we must travel backward in time. Before Earth, before the planets, perhaps even before the sun itself, into a cold region of the galaxy where a different star was being born, and the first frozen grains of 3I/Atlas were beginning to gather in the dark. To understand 3I/Atlas, we have to leave the solar system behind, not physically, not with a spacecraft, but with imagination guided by science. We have to move backward through time, beyond the moment it was discovered, beyond the moment it entered the sun's light, beyond even the long, silent journey it made between the stars. We have to ask where such an object could have begun. And the first honest answer is this: we do not know. We do not know the name of the star that once held it. We do not know exactly when it formed. We do not know whether its parent star still shines somewhere in the Milky Way, or whether that star has already changed beyond recognition. It may still be out there, quiet and distant, surrounded by planets that no human telescope has yet seen clearly. Or it may be gone. It may have expanded, collapsed, faded, or drifted far from the place where 3I/Atlas first took shape. The galaxy does not preserve simple maps for objects that wander for millions or billions of years. Stars move. Clouds disperse. Orbits shift. Gravity slowly mixes the histories of everything. So when 3I/Atlas arrived in our solar system, it did not arrive with a label. It did not carry the name of its home. It carried something subtler. Chemistry, the quiet fingerprint of the environment where it formed. And that fingerprint points us toward a place that was cold, very cold. Colder than most places where we imagine worlds beginning. A place where water could freeze hard into ice, where carbon-bearing molecules could settle into grains, where dust and gas could come together slowly in the darkness around a young star. To picture that birthplace, imagine a region of space long before any planet had fully formed. There is no Earth there, no blue ocean, no forest, no moonlit night, only a young star, still wrapped in the material that gave birth to it. Around it spins a wide disk of gas and dust, a protoplanetary disk. It is the kind of disk from which planets, moons, asteroids, and comets can eventually emerge. Closer to the young star, the disk is warmer. Dust grains collide. Metals and rocky minerals gather. The seeds of inner planets begin to form. But far out, in the dimmer, colder regions of the disk, the story is different. There, sunlight is weak. Heat is scarce. Volatile molecules, water, carbon monoxide, carbon dioxide, methane, and other ices can freeze onto tiny dust grains. Each grain becomes a little archive, a microscopic record of temperature, pressure, radiation, and chemistry. Over time, these icy grains bump into one another. They stick, they grow. Small clusters become larger clumps. Larger clumps become kilometer-scale bodies. These are planetesimals, the building blocks of planets and the ancestors of comets. Some of them may one day become part of a planet. Some may be shattered. Some may remain in distant reservoirs of ice. And some, like 3I/Atlas, may eventually be thrown away from their star entirely. But before that exile, before the long wandering, there was formation. There was a place where its first grains came together, and that place may have been very different from the early solar system. This is one of the most important ideas in the story. 3I/Atlas is not only interesting because it came from outside. It is interesting because it may have formed under conditions unlike those that shape the comets of our own sun. Scientists look for those differences in the ratios of elements and isotopes. An isotope is a version of an element with a slightly different weight. Hydrogen, for example, is the simplest element in the universe. But deuterium is a heavier form of hydrogen. It has the same basic identity, but with an extra neutron in its nucleus. This tiny difference matters, because in the cold chemistry of space, the ratio between ordinary hydrogen and deuterium can change depending on the environment. In very cold regions, deuterium can become more concentrated in certain molecules, including water. So when scientists find water ice with a high amount of deuterium, It can suggest that the water formed in an especially cold environment or in a chemical setting different from the one we know in our own solar system. That is why 3I/Atlas is so valuable. Its ice may remember temperatures that no thermometer ever measured. Its molecules may preserve a clue from the place where it formed. Its chemistry may tell us that its birthplace was colder, older, or chemically different from the disk that gave birth to Earth and the other planets around the Sun. And if that is true, then 3I/Atlas is not just a comet. It is a sample of another beginning. A beginning we cannot visit. A beginning that happened around another star, in another region of the galaxy, under conditions that may never be repeated in exactly the same way. This is where the story becomes almost dreamlike, because when we look at 3I/Atlas, we are not really seeing only the object itself. We are seeing a trace of a vanished environment, the cold outer edge of another young solar system, the dusty disk around another newborn star, the first slow gathering of ice and carbon in a place far from any sunlight we know. No one was there to witness it. There were no telescopes, no planets with life, no names. Only physics, only gravity, only tiny grains drifting through a disk, colliding gently, sticking together, and becoming something larger. Over time, those grains built a body strong enough to survive the violence of its young system. And that body, or part of it, would one day become the object we call 3I/Atlas. But even this picture is only a reconstruction, a careful scientific guess built from clues. We should be humble about it. The universe rarely gives us complete stories. It gives us fragments, a motion across the sky, a spectrum of light, a ratio of hydrogen to deuterium, a trace of carbon, a faint coma around a distant nucleus. From these fragments, scientists build the most reasonable picture they can. Not fantasy, not certainty, but evidence shaped into understanding. And the evidence suggests that 3I/Atlas may have come from a place very different from home. Maybe it formed in a colder region of a planetary disk than the comets we know best. Maybe its parent system was born in a part of the Milky Way with a different chemical history. Maybe the cloud that created it was older, less enriched by generations of stars, carrying fewer heavy elements than the cloud that formed our sun. If so, then 3I/Atlas may be a relic from a chapter of galactic history much earlier than our own. Think about that for a moment. Our sun is ancient by human standards. It has been shining for about 4.6 billion years. It was already old when the first life on Earth appeared. It was already old when the first continents formed. It was already old when the first eyes opened in Earth's oceans and looked at light. But the Milky Way is older still. Long before our sun was born, other stars lived and died. Other disks formed. Other icy bodies gathered in the dark. Some of them became planets. Some became comets. Some were scattered into deep space. 3I/Atlas may be one of those scattered remnants. A frozen piece of a planetary system that began before ours. Not necessarily older than everything we know. Not certainly as old as the galaxy itself. But possibly older than the sun. Possibly shaped by a time and place that no human eye will ever see directly. This is why it feels so haunting. Because it reminds us that the solar system is not the center of the story. It is one chapter, one harbor, one warm region around one star. But beyond it, the galaxy has been building worlds for billions of years. Worlds around red dwarfs. Worlds around stars larger and brighter than the sun. Worlds in crowded clusters. Worlds in cold, quiet outskirts. And around many of those stars, small icy bodies must have formed by the trillions. Some remained. Some collided. Some became part of planets. And some were thrown away, becoming silent travelers between stars. 3I/Atlas may have started as one of countless icy fragments in a young system far from here. It may have spent its earliest years circling a star it would eventually lose. Perhaps it once moved among other comet-like bodies, all sharing the same frozen birthplace. Perhaps, from its surface, if there had been eyes to see, its parent star would have looked like a small bright sun in a dusty sky. But no such eyes existed. There was only ice, only dust, only the slow mathematics of gravity. Then the young system changed. Planets grew. Their gravity strengthened. The quiet disk became a place of motion and disturbance. Small bodies were pulled, scattered, redirected. For a while, 3I/Atlas may have remained safe in the outer cold. But in a young planetary system, safety can be temporary. A distant object can be nudged inward. A small shift can become a large one. A path can cross the orbit of a giant planet. And when a small icy body meets a giant world, the result can be permanent. Not a collision, not destruction, just a gravitational encounter. A silent exchange of energy. A single close passage that changes everything. That may be how 3I/Atlas lost its home. It was born in cold darkness around another star. But it did not stay there. Something in that system moved it. Something gave it speed. Something opened its orbit until the star that once held it could hold it no longer. And from that moment on, 3I/Atlas became what we met billions of years later. Not a resident of any solar system, not a member of any planetary family, but a wanderer, a piece of ancient ice thrown into the dark ocean between stars. And to understand that exile, we must look more closely at the quiet power that can remove a world from its home without ever touching it. Gravity. Gravity does not need to touch. It does not need a surface. It does not need a hand. It reaches silently across empty space, shaping the paths of planets, moons, asteroids, dust, and comets. It holds worlds together. And sometimes, it sends them away forever. To understand how 3I/Atlas may have become an interstellar wanderer, imagine a young planetary system long before it became stable. Not the calm, clock-like solar system we see today. Not planets moving in familiar paths. Not moons settled into regular orbits. But a young system still under construction. A star has recently formed at the center, surrounded by a wide disk of gas, dust, rock, and ice. Inside that disk, countless small bodies are growing. Some are only grains, some are pebbles, some are mountain-sized fragments, some are already becoming the cores of future planets. Everything is moving. Everything is pulling on everything else. The system is beautiful, but it is not peaceful. In the inner regions, rocky worlds may be forming from metals and silicates. In the outer regions, where temperatures are far colder, icy bodies gather in the dim light. There, water, carbon dioxide, carbon monoxide, methane, and other volatile substances can freeze and become part of small comet-like worlds. This is where an object like 3I/Atlas may have begun, far from its parent star. Cold, small, ordinary, at first, just one frozen body among many. It may have followed a quiet orbit for a while, circling its young star in the outer darkness. Around it, other icy fragments moved in similar paths. Some were larger, some were smaller, some collided and broke apart, some merged and grew. For a time, it belonged. It was part of a system, part of a family. But young planetary systems do not always remain gentle. As larger planets form, especially giant planets, their gravity begins to dominate the space around them. A giant planet is not only a world, it is a sculptor. It clears paths, it stirs debris, it pulls small bodies inward, it throws others outward. Jupiter did this in our own solar system. Long ago, Its enormous gravity helped shape the asteroid belt, redirected comets, and influenced the architecture of the planets. In other star systems, giant planets may do the same, sometimes even more violently. A small comet does not need to collide with such a planet to have its life changed. It only needs to pass nearby. Not close enough to crash, just close enough for gravity to take hold. Picture a small icy body drifting along its orbit. For thousands of years, maybe millions, its path is stable. Then, slowly, perhaps because of the pull of another object, its orbit shifts. It comes a little closer to the region controlled by a giant planet. At first, the change is small, a gentle nudge, a slight bend. But in space, small changes can grow across time. Eventually, the comet passes near the giant planet, and in that moment, its future is rewritten. From the comet's point of view, nothing touches it. There is no explosion, no bright flash, no sound. But the planet's gravity pulls on it with enormous strength. The comet accelerates, its path bends. Energy is exchanged between the small body and the massive planet. The planet barely notices. A giant world is too massive to be changed in any visible way by one small comet. But the comet notices everything. Its orbit stretches, its speed changes, its connection to the star weakens. And if the encounter is strong enough, the comet gains more speed than it needs to remain bound. The orbit opens. The path no longer curves back. The comet has escaped. From that point forward, its parent star is no longer a home. It is only a light fading behind it. This may sound dramatic, but it is one of the most natural processes in planetary systems. When planets form, they do not simply create order, they also create exile. They scatter the leftover material. They decide which small bodies remain, which fall inward, which collide, and which are thrown out into the galaxy. In that sense, interstellar space may be filled with lost fragments, frozen leftovers from other stars, small worlds that never became planets. Comets that were born in one system and then abandoned to the dark. 3I/Atlas may be one of them. A body formed in the cold edge of another planetary system, then sent away by a gravitational encounter so quiet that no one could have witnessed it except the objects involved. And after that encounter, everything changed. There would be no more return, no orbit bringing it back home, no familiar star growing brighter, then dimmer, then brighter again. No cycle, only departure. If it had a surface pointed back toward its parent star, that star would have slowly shrunk into the background. At first, perhaps it still would have been the brightest light in the sky. Then, over time, it would have become one bright star among others. Then, just another point. Then a memory written only in motion. This is one of the loneliest ideas in astronomy. A comet does not know it has been exiled. It does not feel loss. It does not understand home. But we do. And so when we imagine a body like 3I/Atlas being thrown into interstellar space, we cannot help but give the event a kind of sadness. A small frozen world, once part of a system, is released into the galaxy, not because of purpose, not because of punishment, only because gravity allowed no other ending. And once it leaves, it enters a very different kind of existence. Inside a solar system, even a distant comet has a rhythm. It moves around a star. It belongs to a structure. Its path has a center. Outside a solar system, there is no nearby center. No warm sun, no seasons, no regular return. There is only motion through a sea of stars. The distances become enormous. The light becomes thin. The temperature falls. The surface settles into silence. Any gases that once escaped from its ice freeze again. Dust rests on its crust. Chemical reactions slow almost to nothing. Time stretches until millions of years become only part of the journey. And still, it moves. A body like 3I/Atlas would travel through the galaxy under the combined gravity of many stars, clouds, and the Milky Way itself. It might pass near other systems without entering them deeply. It might cross regions of interstellar gas so thin they would seem empty by any human measure. It might spend ages without coming close enough to any star to awaken. Most of its life would be darkness. This is why the moment it entered our solar system was so important. Because for a long time, perhaps an unimaginably long time, 3I/Atlas may have been inactive, frozen, quiet, almost unchanged beneath its outer surface. Then, after crossing the deep between stars, it came near the sun. And the sun did what stars do. It gave heat. It gave light. It reached the ancient ice and began to wake it. But before that awakening, before the coma, before Webb could read its chemistry, before astronomers could measure the gases rising from its surface, there was the long journey itself. The interstellar night, a journey so vast that no human lifetime could hold it. If 3I/Atlas was ejected from another system billions of years ago, then it traveled while Earth was changing beyond recognition. It traveled while continents shifted, oceans formed and reformed, life evolved from simple cells into forests, animals, and eventually human beings. It may have been moving through the galaxy before anyone looked up and named the stars, before the first telescope, before the first city, before the first fire, before our species existed at all. And then, by chance, its path crossed the path of a civilization capable of noticing it. That is the astonishing part. Not only that it was thrown away, not only that it survived, but that it arrived here during the brief window when Earth had machines watching the sky. For most of human history, it would have passed unseen. For most of Earth's history, there was no one to notice. But this time, there were telescopes, there were sky surveys, there were astronomers, there was Webb, and so the wanderer did not pass completely in silence. For a moment, the galaxy's lost fragment became visible. But to understand what that long exile may have done to 3I/Atlas, we have to follow it into the dark between the stars. Because interstellar space is not simply empty. It is quiet, yes. Cold, yes. But over enough time, even the quiet can change a world. Interstellar space is often described as empty, but empty is not quite the right word. It is not empty in the way a room is empty after the lights go out. It is not empty in the way a desert road is empty at midnight. It is something far larger, far colder, and far more patient. Between the stars, there are still atoms, a few particles drifting through enormous volumes of space. There are magnetic fields so faint they seem almost like whispers. There are cosmic rays traveling close to the speed of light. There are old photons, ancient dust grains, and thin clouds of gas stretched across distances too large for the human mind to hold. But compared with the warmth of a planetary system, compared with the light around a star, interstellar space is almost nothing. A deep ocean of darkness. And somewhere in that ocean, 3I/Atlas traveled alone. After it was thrown from its original system, its parent star would have slowly fallen behind. At first, that star may have still been bright. It may have been the one clear light in the sky of this small frozen body, the center it once knew, the source of the warmth that shaped its earliest history. But as the distance grew, the star became smaller, less powerful, less personal. Eventually, it was only one point among countless others, and then, perhaps, not even recognizable. From that moment onward, 3I/Atlas had no home in the ordinary sense. No star close enough to dominate its sky. No orbit with a return. No morning. No evening. No season. Only motion. A slow, endless crossing through the spaces between suns. For a comet inside a solar system, time has a rhythm. Even if the orbit is long, there is still a cycle. Far from the star, the comet freezes. Near the star, it wakes. Its ice becomes gas. A coma forms. A tail may stretch behind it. Then it leaves again, returning to cold and darkness until the next passage. But for an interstellar comet, there may be no next passage for a very long time. Maybe no nearby star for millions of years. Maybe no warmth strong enough to wake the ice. Maybe only darkness, radiation, and time. In that long night, 3I/Atlas would have been almost perfectly silent. No wind moved across its surface. No rain fell. No waves broke against its cliffs. No atmosphere carried sound. If small grains of dust struck it, they did so in silence. If cosmic rays altered its outer layers molecule by molecule, they did so without light, without drama, without any sign visible from far away. The surface may have slowly changed. A skin of processed material may have formed over the older ice below, darkened by radiation, hardened by time, altered by the slow touch of the galaxy itself. This is one of the strange truths about ancient objects in space. They can preserve the past, but they are not untouched by the journey. The deeper material may remember the birthplace, the original ice, the ancient chemistry, the cold conditions of another star system, but the surface may remember the road, the long exposure to cosmic rays, the impacts of dust, the endless freeze of interstellar space. So 3I/Atlas may have become two stories layered together. Inside, a memory of where it was born. Outside, a memory of everything it survived. Imagine it drifting through the Milky Way, not quickly by human feeling, but incredibly fast by the scale of ordinary life, moving across the galaxy while stars themselves also moved. The sun was orbiting the center of the Milky Way. Other stars were shifting in their own long paths. Clouds of gas were forming new suns. Old stars were dying. Spiral arms were slowly turning like vast, luminous currents. And through all of this, a small, icy object continued forward. No destination. No awareness. Only a trajectory given to it long ago. It may have passed through regions where the stars were sparse and dim. It may have crossed the faint outer influence of other systems without ever coming close enough to be captured. It may have moved for ages through blackness so complete that the nearest star would have looked like nothing more than a bright dot in an endless field. If there had been a way to stand on its surface, the sky would not have looked like our night sky. There would be no moon, no planets shining nearby, no familiar constellations holding their shapes across human history. Only stars in every direction, cold and distant, arranged according to whatever point in the galaxy the comet was passing through at that time. And the silence would have been absolute. This is where the story of 3I/Atlas becomes almost impossible to measure emotionally, because we can say millions of years, we can say billions of years, but those words are too clean, too small. A million years is longer than civilization, longer than agriculture, longer than language as we know it. A billion years reaches back before almost everything familiar on Earth. If 3I/Atlas wandered for even a fraction of such time, then its journey was older than mountains, older than coastlines, older than the entire story of human beings. While it moved, Earth changed. Oceans rose and fell. Continents broke apart and came together. Life climbed from water onto land. Forests appeared. Species vanished. Ice ages came and went. And still, somewhere beyond the warmth of any nearby star, this small frozen traveler continued through the dark. It did not know Earth existed. It did not know the sun was waiting somewhere ahead. It did not know that one day, on a small blue planet, a species would build telescopes, launch observatories into space, and learn to read the chemistry of light. It simply moved. That is one of the most calming and humbling parts of the universe. So much happens without hurry. The galaxy does not rush. Stars take millions of years to form. Planets gather slowly from dust. Comets sleep through ages. And sometimes, a body that has wandered longer than humanity has existed crosses our sky for only a brief moment. A few months of visibility after an ocean of time. For most of its journey, 3I/Atlas would have been invisible to us even if we had been looking in the right direction. Too small, too dark, too far from any star to glow. A comet becomes visible when a star wakes it. Until then, it is more like a dark seed drifting through space, carrying frozen material inside itself, waiting without intention for warmth it may never find. And yet, the warmth did come, not from its original star, not from the system that made it, but from ours. After an unknown age in the interstellar night, the path of 3I/Atlas began to bring it toward a new light. At first, the sun would have been only one star among many. A yellow-white point in the distance. Nothing special from far away. Just another star in the galaxy. But as the comet approached, that point slowly brightened. The sun's gravity began to shape its path more strongly. The surrounding darkness changed. The outermost regions of the solar system opened ahead. First, perhaps, the distant realm beyond Neptune. Then the wide, faint reaches where icy bodies orbit in silence. Then the region where the planets become more tightly arranged around the central star. The traveler was entering a new harbor, not to stay, not to join, only to pass through. But even a brief passage near a star can transform an icy body. Light that seems gentle from Earth can be powerful to ancient ice. Heat reaches the surface. Frozen molecules begin to move. The outer layers respond. After an age of stillness, the comet begins to change. This is the moment when a silent object becomes visible, when the dark seed becomes a comet, when ancient ice, preserved through the long night between stars, finally begins to breathe into space. And for 3I/Atlas, this awakening was more than a physical change. It was the moment that made its secrets available. As sunlight touched its surface, gas and dust began to escape. A faint atmosphere, called a coma, formed around the nucleus. Molecules that had been locked in frozen darkness were released into space, where telescopes could observe them. The comet did not choose to reveal itself, but the sun made revelation possible. For astronomers, this was the precious window. The rare chance. A visitor from another star had entered the warmth of our solar system, and its ancient ice was beginning to speak in the only language it had. Light, chemistry, motion, a faint glow against the dark. The long interstellar night was ending, at least for a while. Ahead was the sun, behind was the galaxy, and around this small frozen traveler, after perhaps millions or billions of years of silence, the first traces of gas began to rise. For most of its journey, 3I/Atlas had been quiet. It had crossed the darkness between stars with almost no warmth touching its surface. It had moved through a region where sunlight from any single star was weak, where ice could remain frozen for ages, where molecules could sleep inside a body that no one had ever seen. But the solar system is not dark in the same way. At its center is the sun, a star ordinary by the standards of the galaxy, but overwhelming to anything that has spent a long time in interstellar night. From far away, the sun was only another point of light, a bright star among billions. But as 3I/Atlas approached, that point became something else, a source of heat, a source of gravity, a source of change. The visitor did not slow down enough to stay. It was still moving on its open path, still passing through the solar system like a traveler crossing a quiet harbor. But even a traveler who does not stop can be changed by the place it passes through. And the sun began to change 3I/Atlas. At first, the change would have been subtle. A little more sunlight reaching the surface. A slight rise in temperature. Tiny regions of ancient ice beginning to respond after a long, frozen sleep. To us, sunlight feels familiar. It warms skin. It lights mornings. It turns oceans silver and makes shadows move across the ground. But to a comet, sunlight is not gentle. It is an awakening force. Comets are made of materials that can remain frozen in deep space. Water ice, carbon dioxide ice, carbon monoxide, dust, and other volatile compounds. Far from the sun, these materials can stay locked in place. They are quiet, solid, hidden. But as a comet comes closer to a star, the surface warms, and some of that ice begins to change directly into gas. This process is called sublimation. It is one of the most important transformations in a comet's life. The ice does not melt into liquid water first. In the near vacuum of space, it can go straight from solid to vapor. Molecules that were locked in frozen darkness escape into the surrounding space, carrying dust with them. Slowly, a cloud begins to form, a faint atmosphere around a tiny world. This cloud is called a coma, and it is one of the reasons a comet can become visible. The nucleus itself may be small, dark, and difficult to see, but when gas and dust surround it, sunlight scatters through that material, and the comet begins to glow. Not like a star, not from its own power, but from reflected sunlight and from the activity of its escaping gases. A sleeping body becomes a visible one. A hidden traveler becomes a comet. For 3I/Atlas, this awakening was especially meaningful, because this was not just any comet returning to the sun after a long orbit. This was a comet from outside the solar system. Its ice had not formed in the disk that created Earth. Its chemistry may not have followed the same path as the chemistry of our own comets. Its frozen material may have been shaped by another star, another cloud, another chapter of the Milky Way. And now, for the first time since humans had noticed it, that material was being released into space. The sun was opening the archive. Imagine an ancient book sealed in ice. For billions of years, perhaps, no one reads it. It drifts in darkness. Its pages remain closed. Its language is not written in ink, but in atoms. Hydrogen, deuterium, carbon, oxygen, dust. Then, after an endless journey, the book passes near a fire. The ice begins to loosen. A few pages open. Not all of them. Never all of them. But enough for us to glimpse the story. That is what the sun did to 3I/Atlas. It did not create the mystery. It revealed it. As 3I/Atlas moved deeper into the solar system, its speed increased under the pull of the sun's gravity. Like a stone rolling down the invisible slope of space-time, the comet moved faster as it came closer to the star. It was not falling into the sun. It was not being captured. It was being bent and accelerated, following the path that gravity allowed. At its closest approach to the sun, known as perihelion, 3I/Atlas came to roughly the distance of Mars's orbit, a little outside it. Earth was far away, safely on another part of its orbit. There was no danger, no collision course, no catastrophe waiting in the sky. The importance of this passage was not danger. It was access. A comet becomes most revealing when sunlight is strong enough to wake its volatile materials. If 3I/Atlas had passed too far from the sun, it might have remained too cold, too quiet, too inactive for detailed study. Its surface might have stayed sealed. Its chemistry might have remained hidden. But it came close enough for heat to reach the ancient ice, close enough for gas to rise, close enough for telescopes to watch the coma grow around it. And in that coma, the comet carried pieces of its interior outward. This is the great gift of comet activity. We cannot easily drill into the nucleus of an interstellar comet. We cannot land on it. We cannot collect samples and bring them back to Earth. Its visit is too brief, its speed too great, its origin too remote. But the comet helps us. As it warms, it releases material by itself. Gas escapes from beneath or within the surface. Dust lifts away. Molecules enter the coma, where they can interact with sunlight and become visible to instruments. The comet, in a sense, becomes its own sample return mission, not by sending material to Earth, but by spreading its chemistry into space, where light can carry the information to us. And this is why astronomers watched 3I/Atlas so carefully. Every change mattered. Its brightness, its shape, its coma, its speed, the tiny effects of outgassing on its trajectory, the gases released from its ice. Each detail was part of a larger question. What is this visitor made of? And what does that tell us about the place it came from? For ordinary comets in our solar system, these questions are already powerful. Comets are often called leftovers from the formation of the planets. They preserve material from the early solar system, from the time before Earth became Earth. But 3I/Atlas offered something rarer. It might preserve material from another planetary system entirely. The coma around it was not only a cloud, it was a temporary bridge between star systems, a way for matter formed around another star to be studied from our own. For a short time, the space around 3I/Atlas carried molecules that may have been locked away since before the Sun existed, or at least since before this object began its long exile. Those molecules had traveled through interstellar darkness. They had survived radiation. They had remained frozen under a surface altered by time. Then sunlight touched them, and they escaped. Some moved away into space. Some were pushed by solar radiation. Some became part of the faint glow surrounding the nucleus, and some left signatures in the light that telescopes could read. This is the moment where the story begins to shift. Until now, 3I/Atlas had been understood mainly through motion. Its orbit told us it came from beyond the solar system. Its speed told us it was not bound to the Sun. Its path told us it was only passing through. But motion can only tell part of the story. A path can tell us that a traveler came from far away. It cannot tell us what the traveler carries. It cannot tell us the weather of its birthplace. It cannot tell us whether its ice formed in a cold disk, a dense molecular cloud, or a region of the galaxy unlike the one that produced our Sun. For that, scientists needed chemistry. They needed to read the gases. They needed to separate the light. And that required some of the most powerful instruments humanity has ever built. The Sun had awakened 3I/Atlas. But the Sun alone could not explain it. For that, we needed eyes beyond Earth. Telescopes capable of seeing faint signals in infrared light. Instruments sensitive enough to detect molecular fingerprints in the coma of a fast-moving visitor from another star. The comet had entered the light. The ice had begun to speak. Now the question was whether we could understand its language. And above Earth, far from the warmth and turbulence of our atmosphere, the James Webb Space Telescope was waiting. Not to chase the comet, not to touch it, but to do something almost as astonishing, to read the memory of another star system hidden inside a cloud of gas around a passing piece of ancient ice. The Sun had awakened the ice, but awakening was only the first step. A comet can glow, it can grow a coma, it can release gas and dust into space. It can become brighter as sunlight warms its surface. But to understand what it is made of, we need more than a beautiful image. We need to read the light. That is what the James Webb Space Telescope was built to do. Not only to see farther, not only to look deeper into the universe, but to separate light into its hidden colors, and use those colors to find the fingerprints of matter. When Webb looked at 3I/Atlas, it was not simply looking at a faint comet passing through the solar system. It was looking at a cloud of gas surrounding a visitor from another star. A cloud made from ancient ice that had begun to escape into space. And inside that cloud, there were clues. Every molecule interacts with light in its own way. Water leaves one kind of signature. Carbon dioxide leaves another. Carbon monoxide, methane, and other gases each leave their own patterns. To the human eye, the coma of a comet may look like a soft glow. But to a spectrograph, that glow is full of structure. It is not just light. It is a message written in wavelengths, a spectrum. Imagine a quiet piece of music, where every instrument plays a different note. If you listen only from far away, you may hear one soft sound. But if you separate the sound carefully, you can tell which notes are present. You can hear the violin, the cello, the piano, the deep vibration underneath. Webb does something like that with light. It takes the light from an object and spreads it out. Then scientists look for the missing and glowing pieces, the places where molecules have absorbed or emitted energy. Those patterns become evidence. They tell us what is there. They tell us what kind of ice has become gas. They tell us what materials were locked inside the comet before the sun warmed it. And because 3I/Atlas came from outside our solar system, those materials were especially important. They were not simply comet gases. They were traces from another planetary system. For most of human history, such a thing was impossible to study. If we wanted to understand matter from around another star, we had to observe that star system from far away. We could watch dust disks. We could measure starlight. We could detect exoplanets only by the tiny shadows they cast, or by the slight wobble they caused in their stars. But 3I/Atlas changed the scale of the question. It brought a physical piece of another system into our neighborhood, not close enough to touch, not close enough to collect, but close enough for light to carry its chemistry to us. This is why Webb mattered. The comet's visit was brief. Its path was open. It would not return. If scientists wanted to understand it, they had to use the short window when the sun had made its gases visible. And Webb gave them one of the clearest ways to do that. As the telescope studied the coma of 3I/Atlas, it detected chemical signs that did not match the familiar pattern of comets born in our own solar system. One of the most important clues was deuterium. Deuterium is sometimes called heavy hydrogen. Ordinary hydrogen is the simplest atom, with one proton. Deuterium is still hydrogen, but it carries an extra neutron. That makes it heavier. This may sound like a tiny difference, and it is. But in the chemistry of cold space, tiny differences can become powerful clues. Water made with deuterium is often called heavy water. It behaves much like ordinary water, but its presence in high amounts can reveal something about the environment where that water formed. In very cold places, certain chemical reactions can enrich molecules with deuterium. So when scientists find water with unusually high deuterium compared to ordinary hydrogen, they begin to ask whether that water formed in an extremely cold region or whether it avoided being warmed and reprocessed over time. In 3I/Atlas, the deuterium level was far higher than what scientists usually see in comets from our solar system. This was not a small difference. It was a signal that stood out, a chemical whisper from somewhere colder than home. The implication is not that 3I/Atlas is unnatural. It is not that it was built. It is not that it carries some artificial secret. The real mystery is more ancient and more beautiful. Its water may have formed in conditions very different from the conditions that shape the icy bodies around our sun. Perhaps in a colder disk. Perhaps in a colder cloud. Perhaps in a system born earlier in the history of the Milky Way, when the mixture of elements was not exactly the same as it is in our local neighborhood today. This is where chemistry becomes time travel. The atoms in the coma of 3I/Atlas were not only telling us what the comet is, they were hinting at where, and perhaps when, it was made. Carbon offered another clue. Carbon is one of the great building blocks of cosmic chemistry. It is found in carbon dioxide, carbon monoxide, methane, organic molecules, dust grains, and eventually in the chemistry of life itself. But carbon also has isotopes. Different versions of carbon can appear in different ratios, depending on the history of the material. In 3I/Atlas, the carbon ratios measured in gases like carbon dioxide and carbon monoxide were also unusual compared with typical values from the solar system. Again, the meaning was not simple. One number cannot tell the entire history of a comet. But together, the clues began to form a picture. High deuterium, unusual carbon ratios, volatile gases released by solar heating, a cometary body traveling on a path from beyond the sun. The story became harder to ignore. 3I/Atlas was not only an interstellar visitor because of its orbit. Its chemistry also seemed to carry the mark of another home, a colder home, a different home, maybe an older home. And then there was methane. Methane is a fragile, volatile molecule. It does not need much warmth to escape from ice. If it is exposed near the surface of a comet, sunlight can drive it away relatively easily. So when Webb detected methane from 3I/Atlas, scientists had to think carefully about what that meant. If methane appeared later, after the comet had already passed close to the sun, it could suggest that some of it had been buried beneath the surface, protected for a time, hidden below the outer layer. Then, as heat moved deeper, that buried ice began to release gas. This gives us a picture of the comet as a layered object. The outer surface, changed by the long journey. The deeper ice, more protected. And somewhere within it, ancient, volatile materials that had survived until the sun reached them. That is why the coma of 3I/Atlas was so valuable. It was not a perfect window into the entire object. Comets are complicated. Their surfaces can be altered by radiation. Their activity can come from specific regions. Gas can escape unevenly. Dust can hide things. Sunlight can change what is released and when. But even an imperfect window is precious when the object will never return. Webb was reading what the comet chose to reveal through physics. Not by intention, not by design, but by heat, sublimation, and light. And the result was astonishing. For a brief moment, humanity was studying the chemistry of another planetary system without ever leaving its own. The telescope did not travel to another star. It did not cross light years. It did not chase the comet back to its birthplace. Instead, the birthplace came to us in fragments, in molecules, in heavy hydrogen, in carbon, in methane, in a faint coma around a small body moving too fast to stay. This is the quiet power of astronomy. We cannot hold most of the universe in our hands. We cannot visit most of the places we study. We cannot fly to the cold disk where 3I/Atlas was born. We cannot rewind the galaxy to watch its first grains come together. We cannot see the giant planet that may have thrown it away, or the star that may once have warmed its early orbit. But we can read light, and sometimes light is enough. Enough to know that the ice is unusual. Enough to know that the chemistry is not like home. Enough to know that this visitor carried a memory from beyond the sun. As Webb studied 3I/Atlas, the comet continued moving. It did not pause for us. It did not slow down so we could understand it better. Every day, it was farther along its path. Every day, the observing window changed. Every day, the chance became a little more temporary. That is part of what makes the discovery feel so fragile. The object had traveled through darkness for an unknown span of time, perhaps longer than the age of our entire species by an almost unimaginable amount. Then it entered the solar system during the brief era when Earth had the instruments to notice it. The sun warmed it. Its gases rose. Webb read the light. And then, almost as soon as the story became visible, the visitor was already leaving. But the data would remain. Long after 3I/Atlas faded from view, the spectra would still be here. The measurements would still be studied. The ratios of deuterium and carbon would still be compared with models of cold clouds, young planetary disks, and ancient regions of the Milky Way. The comet itself would vanish, but its chemical memory would stay with us. And that memory points to a larger truth. 3I/Atlas is not only a curiosity, it is a reminder that the galaxy is not made of isolated stories. Material moves. Systems form and scatter their leftovers. Stars build planets, and planets throw small worlds into the dark. Some of those small worlds wander for ages, and once in a while, one of them passes through the light of another star. Our star. For a moment, a fragment of another beginning becomes part of our sky. For a moment, we are allowed to read it, and then it goes on. So what does this visitor tell us about the galaxy? Maybe it tells us that our solar system is only one version of a much larger pattern. Maybe it tells us that water, carbon, ice, and planet-forming material can have very different histories around different stars. Maybe it tells us that the Milky Way is full of hidden archives, drifting between suns, waiting for the rare chance to be warmed and read. And maybe, somewhere out there right now, countless other frozen visitors are moving through the dark. Some will never pass close to a star again. Some will fall into systems where no one is watching. And some, perhaps, will one day cross another sky, around another world, where another kind of observer may look up and wonder where they came from. 3I/Atlas was small. In the scale of the solar system, it was almost nothing. Not a planet, not a moon, not a giant asteroid capable of reshaping worlds. Just a faint, icy body, moving through the dark, briefly warmed by the sun, briefly visible to our telescopes, briefly close enough for Webb to read the gases rising from its surface. And yet, this small object carried a question larger than itself. How different are other planetary systems from our own? For most of human history, the solar system was the only planetary system we knew. The sun, the planets, the moons, the asteroids, the comets. This was our entire example of how worlds are arranged around a star. We could study the planets in detail. We could watch Jupiter's storms, Saturn's rings, Mars's deserts, Venus's clouds. We could send spacecraft to comets and asteroids and build a history of our own cosmic neighborhood. But there was always a danger in knowing only one example. When you know only one system, it is easy to imagine that it is normal, that this is how planetary systems are supposed to look. A star in the center, small rocky planets close in, gas giants farther out, icy bodies beyond them, comets waiting in the cold. But over the last few decades, astronomy has taught us that the galaxy is far more creative than that. We have found giant planets orbiting extremely close to their stars, worlds so hot that their atmospheres may be stripped away by radiation. We have found planets around small red dwarfs, where the star is dim and long-lived, and the habitable zone lies close enough that a planet's year may last only days or weeks. We have found systems with multiple planets packed tightly together. We have found worlds larger than Earth but smaller than Neptune, a type of planet that does not exist in our solar system at all. And we have found disks of dust and gas around young stars, places where planets may still be forming in real time. All of this has changed our view. The solar system is not the template for everything. It is one arrangement among many, one outcome, one version of how gravity, chemistry, time, and chance can build a family of worlds. 3i/Atlas adds something different to that story. Exoplanets show us other worlds from far away, but an interstellar comet gives us a piece of another system close enough to study as matter, not just as a shadow crossing a star, not just as a wobble in starlight, not just as a distant disk seen through a telescope, but as ice, dust, carbon, water, and gas passing through our own neighborhood. This is why 3i/Atlas matters so much. It is like a sample from another planetary system, delivered by the galaxy itself. No spacecraft had to travel light years to collect it. No mission had to land on a world around another star. The object came to us. Not by design, not for us, but by chance. And chance, in astronomy, can sometimes become a doorway. Through that doorway, scientists could ask whether the building blocks of other systems resemble the building blocks of ours. Are their comets rich in the same kinds of ice? Do they carry water with similar isotope ratios? Do they form in similar temperatures? Do they preserve the same balance of carbon-bearing molecules? Or is each system shaped by its own local history? The answer, suggested by 3i/Atlas, is that other systems may preserve very different chemical stories. Its unusual deuterium and carbon signatures hint that it did not form under the same conditions as familiar comets of the solar system. That does not mean our comets are ordinary, and 3i/Atlas is impossible. It means the galaxy may contain many kinds of beginnings. Some planetary systems may form in cold, dense clouds, where deuterium becomes strongly enriched in water. Some may form in regions with different carbon chemistry. Some may form earlier in the history of the Milky Way, when the galaxy had been enriched by fewer generations of stars. Some may form around stars smaller, larger, younger, older, quieter, or more violent than the Sun. And each of those environments can leave fingerprints in the small icy bodies it produces. Comets are not just debris. They are memory. They remember the temperatures of their formation. They remember the molecules available in the disk. They remember the chemistry of the cloud that collapsed to form the star. They remember, in a quiet and incomplete way, the conditions that existed before planets fully became planets. This is true in our solar system, and 3i/Atlas suggests it is true elsewhere. Every planetary system may have its own frozen archive, a population of icy leftovers orbiting in distant darkness. Some may remain forever bound to their parent stars. Some may be scattered inward, becoming active comets. Some may collide with planets, delivering water or organic materials. And some may be thrown into interstellar space, becoming wanderers between the stars. If that is common, then the galaxy may be filled with invisible travelers. Not a few, not hundreds, but perhaps countless small bodies, drifting through the spaces between suns. Most will never pass near Earth. Most will never be seen. Some may fall into stars. Some may pass through systems with no one watching. Some may sleep in darkness for longer than the lifetime of civilizations. But once in a while, one crosses our path. And when it does, it brings a tiny piece of the galaxy's hidden history with it. This changes the way we imagine interstellar space. It is not only emptiness between stars. It is also a place of exchange. A vast, dark ocean, carrying fragments from one system to another. Every star may lose some of its small worlds. Every planetary system may scatter part of its early material outward, and over billions of years, the Milky Way may become filled with the leftovers of its own planet-making process. The space between stars may be haunted by pieces of unfinished worlds. Frozen seeds that never grew into planets. ancient comets carrying water from distant disks, dark fragments from systems we will never visit. In that sense, 3I/Atlas is not only a visitor, it is evidence of connection. It reminds us that the solar system is not sealed away from the galaxy. The boundary around our sun is real in terms of gravity, but it is not a wall. Objects can cross it. Matter can pass through. A body born around another star can enter our sky, be warmed by our sun, and reveal its chemistry to our telescopes. For a moment, two histories overlap: the history of our solar system and the history of another one. That overlap is brief but powerful, because it lets us compare. Our comets tell us about the early sun. 3I/Atlas tells us that another star system may have formed its icy material differently. Our planets tell us one story of world building. Interstellar objects suggest there are many other stories moving unseen through the galaxy. And perhaps this is the deeper meaning of the discovery. Not that 3I/Atlas gives us a complete answer. It does not. One interstellar comet cannot define the galaxy. It cannot tell us what all other systems are like. It cannot reveal the full history of its own birthplace. It is only one fragment, one traveler, one page torn from a much larger book. But even one page can matter, especially if it comes from a book we have never been able to open before. Before the first interstellar objects were discovered, we knew such wanderers should exist. The physics made sense. Planetary systems should scatter debris. Some of that debris should escape. Some should travel between stars. But knowing something should exist is different from seeing it. Seeing it makes the galaxy feel more physical, more connected, more real. 3I/Atlas was not a theory. It was an object. It crossed the solar system. It responded to the sun. It released gas. It carried measurable chemistry. It moved through the same space as our planets, though at a safe and distant path. And then it continued outward. That may be the most important lesson. The universe is not only something far away. Sometimes, the far away comes close. Not close enough to touch. Not close enough to keep. But close enough to remind us that our solar system is part of a much larger flow of matter and time. The atoms in Earth, the ice in comets, the carbon in distant disks, the dust around young stars, all of it belongs to the same galaxy-wide story. Stars create elements. Clouds gather them. Disks shape them. Planets grow from them. Gravity scatters them. And some fragments wander until they pass through the light of another sun. That is what 3I/Atlas did. It carried a small piece of elsewhere into here, and in doing so, it made the Milky Way feel less like a distant background, and more like a living environment of motion, exchange, and memory. Somewhere beyond Neptune, beyond the fading reach of sunlight, the visitor is already moving away. But the meaning of its visit remains. It tells us that other systems are not just points of light in the night sky. They are places. They have histories. They form ice, dust, planets, and comets. They build, scatter, lose, and remember. And sometimes, one of their lost pieces finds its way into the light of our sun. For a brief moment, the galaxy sends us a sample of another beginning, a frozen witness from beyond our home, a reminder that we are not watching the universe from outside it. We are inside the same story, inside the same galaxy, inside the same long river of matter that carries fragments from star to star. And as 3I/Atlas moved onward, leaving behind its measurements, its spectra, and its quiet mystery, it left us with one final thought. If one visitor has crossed our sky, and another before it, and another before that, then this may be happening all the time. The galaxy may be full of silent travelers, ancient ice, lost worlds, fragments of other beginnings. Most of them will remain unseen, but some will pass close enough for a telescope to notice. And when they do, they will remind us again that the solar system is not alone. It is only one illuminated harbor in a dark and endless sea. And the sea is moving. 3I/Atlas did not come to stay. From the beginning, its path was only a crossing, a brief passage through the realm of the sun. For a little while, it moved through the same solar system that holds Earth. It passed through the light that warms our oceans, our forests, our cities, and our quiet nights. It became active under that light. Its ancient ice released gas. Its coma formed. Its hidden chemistry rose into space. And then, just as slowly as it had arrived, the visitor began to leave. There is something deeply strange about that. For millions, perhaps billions of years, this small, frozen body may have traveled unseen between stars. It moved through darkness with no name, no witness, no nearby sun to wake it. Then, for one brief moment in cosmic time, it entered a region where eyes were waiting. Not human eyes alone, but telescopes, surveys, infrared instruments, machines built by a young civilization on a small planet, orbiting an ordinary star. For a moment, the path of an ancient interstellar object and the path of human curiosity crossed. That is what made the encounter so rare. Not because 3I/Atlas was the largest object in the sky, not because it changed the orbit of planets, not because it brought danger, but because it gave us a chance to know something we could not have known otherwise. A piece of another star system passed through our own, and before it disappeared, it let us read a little of its story. But only a little. Most of 3I/Atlas remains unknown. We do not know the star that formed it. We do not know the planets that may have shaped its early orbit. We do not know the giant world that may have thrown it away. We do not know how long it wandered before reaching us. We do not know how many other stars it passed in silence. We do not know where it will go next. That is part of the beauty of it. The universe rarely gives us complete answers. It gives us fragments. A moving dot, an open path, a faint coma, a spectrum, a strange ratio of atoms, a short window of time. And from those fragments, we build understanding, carefully, humbly, knowing that every answer opens another question. As 3I/Atlas moves away from the sun, it will cool again. The warmth that awakened its ice will fade. The gases will weaken. The coma will thin. The glow will disappear. Eventually, it will become what it was before we found it, a dark, frozen body, moving through interstellar space. Only now, it carries one more chapter in its journey. For a short time, it passed through the solar system. For a short time, it was seen. And somewhere on Earth, people looked at the data and understood that this object did not belong to the sun. It belonged to the galaxy. Long after it fades from our telescopes, its measurements will remain. Scientists will continue to study its light, compare its chemistry, and ask what its ice can tell us about planet formation beyond our home. Its physical body will vanish into the dark, but its memory will stay here, written into human knowledge. And maybe that is the quiet gift of an interstellar visitor. It does not stay. It does not explain itself. It does not arrive with purpose. But it reminds us that our solar system is open to the wider galaxy, that other stars are not only distant points of light, they are places where worlds form, places where ice gathers, places where gravity builds and destroys and scatters, places that may lose small fragments into the dark, sending them on journeys with no planned destination. Somewhere out there, right now, there may be countless other bodies like 3I/Atlas, silent, frozen, invisible, traveling between stars. Some may be older than our sun. Some may carry water from systems very unlike ours. Some may have passed through other planetary systems long before Earth had life. Most will never be seen. They will drift through the galaxy without witness, carrying frozen memories from stars we will never know. But once in a while, one comes close enough for sunlight to wake it, close enough for telescopes to follow it, close enough for us to realize that the universe is not as distant as it seems. Sometimes, the galaxy sends a piece of itself through our sky, and for a brief moment, we are allowed to notice. 3I/Atlas will continue onward, past the planets, past the fading edge of the sun's warmth, past the invisible boundary where our star's influence becomes only one pull among many. Ahead of it is darkness again. More stars, more silence, more time than we can imagine. It will not remember us. It will not return. But we will remember it. A visitor from another star. A frozen archive from another beginning. A small, quiet traveler that entered our solar system, opened a few pages of its ancient story, and then continued into the endless night. And somewhere, far beyond the last glow of the sun, 3I/Atlas will become invisible again. Not gone, only moving on, back into the dark ocean between stars, back into the long river of the Milky Way, carrying its secrets forward, forever.